Question 16. The energy levels of the electron in a hydrogen atom are characterized by a quantum number n. E sub n equals minus h c r over n squared, where h is Planck's constant, c is the speed of light, and r is the Rydberg constant. A. State a formula that relates the wavelength of light to h, c, and E, which is the energy of a photon. So you should know that the energy of a photon is E equals hf. We also know that V equals lambda f, where in our case V, the speed, is the speed of light c, so we can change this for c. And if we sort of combine these two together, you should be able to see that E equals hc over lambda. Part B. Let P and Q be the quantum numbers of the upper and lower energy levels of an electron transition in hydrogen. Find a formula that relates the wavelength of the light emitted in such transitions to P and Q. Okay, let's draw a little diagram. So we have the upper energy level P and the lower energy level Q. And this transition will be some energy, let's call it delta E. And from this equation in part A, we know that delta E will equal hc lambda, because we know that the wavelength of the photon emitted for this transition will be lambda here, which relates to hc and delta E. Okay. So delta E equals the energy at P minus the energy at Q. So using the equation given in the question, we get that this equals minus hcr over P squared minus, so that becomes a plus, hcr over Q squared. Apologies, that's getting quite messy. Let's write this down here. So we get delta E equals hcr into 1 over Q squared minus 1 over P squared, where I've sort of swapped things around to make it look a bit nicer. Okay. What else did we know? We knew that delta E equals hc over lambda, or rather lambda equals hc over delta E. And now it's just a case of doing a bit of manipulation. So hcr, if we put all this together, we get P squared minus Q squared over P squared Q squared is delta E. So then 1 over delta E is 1 over hcr P squared Q squared over P squared minus Q squared. And that means that lambda is hc times by this 1 over delta E, which is 1 over hcr P squared Q squared P squared minus Q squared. Then we get these things all cancel. So what are we left with? We're left with lambda equals P squared Q squared over R P squared minus Q squared. part C. So I've cleared some space and I've got the result from the last part of the question just here, and we'll use that in part C. So here we go, part C. For each of the 3 hydrogen emission line sets shown in the table below, identify the quantum number of its lower energy level Q. Each set of 5 emission lines has the same lower energy level. The first column shows the quantum number of the upper energy level Q relative to the lower energy level. You may assume that P is less than 6 and R is that big number. Okay, so first P is less than 6 implies that Q will equal 1, 2, 3, 4, or 5. Okay, because of these P's here. So then, if we draw a diagram again, we have the lower energy level Q and these upper energy levels P, where P is Q plus 1, Q plus 2, Q plus 3, Q plus 4, and Q plus 5. So that's 5, 4, 3, 2, 1. And these transition wavelengths relate to these sort of transitions here. The question's basically saying for which values of Q do we get these sets, basically. So it's just a case of sort of trial and error, plugging stuff in and seeing what happens. So for Q equals 1, draw a little table. We have P equals 2, 3, 4, 5, etc. And we get lambda if we sub these numbers in to this equation up here. We just sub the numbers in using the R given in the question. For 2, we should get 1 to 1.5 nanometers. For Q equals 1, P equals 2. For Q equals 1, P equals 3, we get 102.5 nanometers. And that is pretty much these numbers right here in set A. So what we can say is for set A, Q equals 1. So that's good. We've done set A. Now we just need to do set B and C. So the next one to test would be Q equals 2. So you'll get, you'll get P equals, so it's plus 1, plus 2, plus 3, plus 5. So this will be P equals 3, 4, 5, and 6. You could work out every single one. You probably should if it was actually the exam, but just for the purposes of showing you sort of the method, I'm not going to bother. I'm just going to say etc. But feel free to do it yourself and you should find you get these numbers. So anyway, for Q equals 2, if you sub in those numbers to your calculator, similar to before, you should get 656.11 nanometers for Q equals 2, P equals 3. But when we look at that number, is 656.11 nanometers either of these two here? No, they're not. So I'm not going to bother calculating more because I know that Q equals 2 does not relate to these sets here. So hopefully that makes sense. We've plugged the numbers in, we can't see the number in the table, therefore Q equals 2 is not applicable here. Next we move on to Q equals 3, which will give us P equals 4, 5, 6. And if we sub in Q equals 3, 2, and P equals 4, just turning the wheel basically, or turning the handle rather. Q equals 3, P equals 4, we get 1874.6 nanometers. Is that in the table again? Nope, it's not in the table, similar to Q equals 2, so I'm not going to bother calculating anymore. What about Q equals 4? That gives us P equals 5 and 6. What do we get? We get that Q equals 5, P equals 4. We get 4050.1 nanometers. 50.1, is that in the table? Looks pretty close to this one. Next, what about P equals 6, Q equals 4? We get 262 points, apologies, 4.4 nanometers. Again, that looks extremely similar to this one here. So I will say that set B is Q equals 4, because to reasonable error, these numbers that we've calculated here are these numbers here. And then turning the handle, if we do Q equals 5, then we get P equals 6. We get 7456 nanometers, which to 3 sig fig gives the value in the table. We ran out of Qs, and it's pretty clear that for Q equals 5, this is set C.